Right, in Concept D, we're going to be applying some of the calculations we've done the last few days to a very specific type of compound called a hydrate. We're going to find that some ionic substances can trap water within their crystalline structures. These are called hydrates, and they have a very specific ratio of water to salts. So for example, barium chloride can be hydrated and contain 2 water molecules that are loosely held. So how we represent that is by putting a 2 in front of the water. Now this dot is just a symbol for a hydrate. We're not multiplying anything across the two compounds. We're just saying that these 2 water molecules are attached to the barium chloride structure. Another great example is something called a sodium alum that can be hydrated, and when it does, it has 12 water molecules, which again you can see by the coefficient 12 in front of water. So some of these salts can become anhydrous by evaporating out the water. And we basically do this where we're going to heat to a constant mass and drive all the water out of what was originally a hydrate to find what was left over with the anhydrous salt. And we're going to see that in some of our practice problems. So one of the things you should be able to do with these hydrates is calculate the percent of water by mass simply using the formula. Very similar to what we did in Concept C. We're going to find that the mass of my water is going to be divided by the total mass of the entire hydrate. So our mass of water, we have 2 waters. I like to personally calculate the mass of water and multiply it by the coefficient. Some students like to break it down into hydrogen and oxygen. We'll talk about some advantages and disadvantages to each tomorrow in class. And then the total mass is going to be the water and the barium chloride. So when we go ahead and do that, we find that the mass of water is 18, and we have 2 molecules of water, so 2 times 18. And the mass of the entire hydrate has a mass of 244.3 grams. When we take that division and multiply by 100, we find that this hydrate is 14.7% water by mass. So you should be able to analyze the chemical formulas using this method. And number 2, we're actually going to get results from a lab. So here we have a 3-gram sample of a hydrated salt. So the 3 grams is the entire hydrated salt, including the water, is heated to a constant mass of 2.32 grams. This is the anhydrous salt after the water has been driven out. What is the percent water by mass of the hydrated salt? Well, first off, we have to know the mass of the part, or the mass of the water. Now, how we're going to do that is we're going to take our hydrated salt, which is our original amount, subtracting out the anhydrous salt, which is what's left over after all the water is driven out. The difference between those, in this case 0.68 grams, is how much water was driven out or evaporated out of my sample. So then going ahead and plugging this in, we have our mass of the water, again divided by the total mass of the hydrate, which means that we're plugging in our 0.68 grams of just the water, dividing by the mass of my original hydrate, which includes that water, which is 3 grams. When I go ahead and do that, I find that in this sample, 22.7% was water by mass. All right, and then finally, this is going to tie in some stuff from our Concept B when we were working, or actually C, when we were working with determining our empirical formulas. We can also do this for hydrates. So you have a 5-gram sample that's heated to a constant mass of 1.85 grams, and we want to find the formula of the hydrate. So instead of finding our subscripts, we're actually using this method to find our coefficients to relate the amount of sodium carbonate to the amount of water in the structure. So here we're going to find that we're going to basically take our anhydrous salt, which is 1.85 grams. Okay, again, this is once all the water has been driven out. We're going to use the GFM and convert it to moles. We're then going to find the mass of the water, just like we did in the previous example, which is the difference between the hydrated form and the anhydrous form, which is 3.15 grams, dividing it by its GFM to get my number of moles. And then just like yesterday, we're going to divide by the smallest amount of moles, which is our sodium carbonate, which gives us a ratio of 1 to 10. Those 2 numbers then get plugged in as coefficients, not as subscripts, because we're doing this a little bit differently. So for every 1 sodium carbonate, I get 10 attached moles of water, and that is it. And if we want to name this, we would name our ionic compound sodium carbonate, and then we're going to use prefixes to show how many waters are attached. So this particular hydrate is called sodium carbonate decahydrate. All right, so we'll work with this quite a bit tomorrow, and we'll be doing a whole lab involving hydrates. Just review those three main types of calculations, and you'll be all set.